Hello, welcome back to Learning with Ms. H. Today we're going to go through our Precambrian Time Part 2. So we're going to take a look at the Precambrian Time a little bit closer, and we're going to go through some notes, and you're going to have one of our not quizzes as your assignment. So let's take a look at that first. We've got the Precambrian short quiz here. If you open that up, you'll see that it is a quiz with several different types of questions in it. Remember that these are, quote, not quizzes. So they're set up as quizzes, but you can take them as many times as you need to. So you've got true, false, you've got some ordering where you're just going to drag these and drop these into the right order, however that might be. And then you've got a fill in the blank where you're going to use your number keys to tell me how much of Earth's history it takes up. Very simple quiz. Should not take you long at all, especially if you've done these slides. So go ahead and grab your notebooks, something to write with. We're going to go through these Precambrian time slides in this video. Remember that you can pause the video anytime you need to finish up on a slide and then restart it. If you don't want to go through the slides with me, you can put me on mute and go through the slides, or if you're in my class, you can go through these. These are posted on Canvas, so you can go through them without the video as well. All right, let's get started. So Precambrian time is everything before the current eon. The current eon is the Phanerozoic eon. In this image, it's represented by the yellowish part of the pie chart, and then the Precambrian is all of the blue here. So you're going to see that it happens from 4.6 billion years ago all the way up to roughly 540 million years ago. This little pie chart says 545. These are estimates. Geologic time is not exact, so roughly 540 million years ago. The beginning of Earth is the beginning of geologic time. So that is when we start the beginning of time for us. It is 88% of Earth's history, so all of this blue is 88% of that pie chart. So 88% of our history of Earth is Precambrian time. If you are in class with me, guarantee that's going to be a test question. They will give you a pie chart. They'll have different amounts of the pie chart filled in with black, and you're going to pick the one that matches this one. So the black should match the blue here, so that you're showing that it is 88% of the time. Guaranteed test question. Simple life is going to start in the oceans during this time, and then it's broken down into 3 eons. Hadean is the earliest one, from the beginning of time to about 4 million years ago. Archaean is the middle, from 4 million years ago to about 2.5 million years ago. And then Proterozoic is the most recent, and it goes from 2.5 million years ago to 540 million years ago, right up to that Cambrian explosion. Hadean is going to be mostly formation of the Earth. Archaean is going to start differentiating when we start getting the continents forming. Towards the end, we're going to start having some single cell life in the oceans, and they're going to start doing photosynthesis, and then we'll start getting more complex life here at the border of the Archaean and the Proterozoic. Our Avalon explosion is going to happen up here in the Proterozoic, and then the Cambrian explosion is right here on the border of Precambrian time and the Phanerozoic eon. So Precambrian begins with the formation of the Earth and ends with the Cambrian explosion. So remember that you can go ahead and pause the video whenever you need to finish up some slides, and then restart it again to pick up with the next one. So this slide, I'm not going to have you guys write this down in your notebooks right now. If these kinds of things help you, you may do that later. This is basically a summary of some of the major events that happen during each time frame of the Precambrian time. So during each eon, this is what's going on. We're going to talk about all of this on the slides coming up, but this is a summary of everything all in one place. So, highlights from the Hadean. When you have slides like this for this lesson today, if it's got yellow, that's something that you really need to focus in on and get written down. The white information is basically supportive information and extra explanations, but the yellow information is the main key points. The Hadean Eon was from 4.6 billion years ago to 4 billion years ago. During that time, this is when the solar system is forming. So the beginning of Earth, the beginning of all of the planets, everything is forming up and starting to become our solar system as we know it. So it starts off with the Solar Nebula. You have all of the dust and the gas in that area. It's going to start coming together and forming things like asteroids and comets and moons and planets. As all of that interstellar dust is coming together or coalescing, that is when the Earth is being formed and it becomes its spherical shaped ball from all of those items crashing into each other. That happens starting with about 4.6 billion years ago, and it takes millions of years. So during that time, Earth gets bombarded by large planetesimals. They join up with the current ball of stuff that is going to become the Earth. It adds to our mass, it adds to our heat. Anytime you have those collisions, it's going to cause heat. As we continue to heat up that way, we're spinning around. Every time we get hit, we spin a little bit differently. All of our mass, because of the intense heat, starts melting. So we get basically, we turn into what is basically a giant ball of fiery molten rock. So if you consider what magma looks like or what lava looks like, think about a planet-sized ball of just that with no solid surface whatsoever. Everything is hot, fiery, molten rock. Because of this, all of the layers are going to separate it out. Less dense layers are going to come towards the surface. More dense layers are going to sink towards the core. So when we form those layers, the iron and nickel are going to go down to the center. They're going to sink to the core of the Earth, and they're going to start solidifying because of the intense heat and pressure down there. So we're going to start getting our solid core. All of the silicate material is going to move out to the mantle area, which is the part that's still the hot, molten, flowy rock. Another connection to astronomy, we talked about Theia, which was the Mars-size planetesimal that hit us to knock all of the material out into our atmosphere that's going to eventually form the moon. So that's going to happen around this time. All of that material goes into orbit around us. It eventually coalesces, creates the moon. That same impact is thought to have caused the Earth to spin faster and start our rotation on our axis. It's thought to have tilted our axis. And then we know that that moon orbiting around us causes changes in tides. And then we got our core, and most of our molten outer area is going to start spinning around that core, and we're going to start developing our magnetic field. Once we get that magnetic field, we can start developing a permanent atmosphere. Up until this point, we originally had a hydrogen-helium atmosphere, but we had no way to hold it in place, so solar winds blew all of that away. So, quick summary. We started off with molten Earth forming 4.6 billion years ago. And then about 4.3 billion years ago, we're going to start having the surface cool. So now we're going to get to the part where we're starting to form that crust, the shell around the molten part of the Earth. Oldest crust rocks are going to be found in Australia and Canada. And then during this time, we start developing our early permanent atmosphere. It's called a primitive atmosphere because there's not really any free oxygen in the atmosphere. It's mostly coming from volcanic eruptions, from all of that magma flowing around. We're going to start getting crust because that magma is going to start cooling, but we still have those volcanic eruptions happening, and we basically get a bunch of volcanic islands. Anytime volcanoes erupt, we get lots of carbon dioxide put out from that, and that's what's going to create most of our atmosphere. As the surface starts cooling and we start developing that shell, we're going to start having that solid surface to collect water. Up until this point, any water that's has hit the magma. It's turned immediately into water vapor. It gets released again from the volcanic eruptions. But now that we're starting to have a solid surface, we can start collecting liquid water in places. So as it cools off enough, some of that water vapor will condense and become liquid water. We can also, in addition to getting it from the volcanic eruptions, we can also get it from deposits from comets. Because remember that comets are basically giant balls of dust and ice. They're basically big snowballs. So as they impact other things out in space, they deposit all of that dust and ice on the surface of whatever they hit. Okay, so again, we're going to stick with only the yellow. So our early atmosphere was hydrogen and helium, but we lost it to solar winds because we did not have a magnetic field at the time. Once we started developing the core and we started spinning around it and developed that magnetic field, we were able to keep an atmosphere in place, and it was mostly nitrogen and carbon dioxide, again from volcanoes and comets. Eventually, we're going to start having photosynthesis occur when we start getting some organisms around. And we're going to take that carbon dioxide and convert it into oxygen. So eventually we are going to get an oxygen atmosphere, just not yet. Our early permanent atmosphere, we had very little oxygen in the atmosphere. It's mostly nitrogen, carbon dioxide. There are some other particles and molecules in there as well. But we would not be able to breathe in this atmosphere. It would be toxic to us and most organisms that we recognize today. At the time, it was organisms that use carbon dioxide and turn it into oxygen. So Eubacteria and Stromatolites. This is about 3.5 billion years ago, and we didn't get fully oxygenated until just under 2 billion years ago. So we are going to be in the Archaean time period here once we get into that area of time. So late Hadean, we're going to have formation of the continents start happening. We have all of this magma. It's basically a molten ball. It's eventually going to cool and start forming a crust. These darker areas are indicating where it's cooling off and starting to solidify. This is going to be the beginning of the formation of the continents. So the very end of the Hadean is going to be where continents start to form, and most of them are going to form during the Archaean. And remember, we cannot have life until we get into the Archaean and we have continents and oceans and start having conditions that are conducive to life. There's no life with no atmosphere. So we're going to move into the Archaean now. It's between 4 billion and 2.5 billion years ago. So that 3.5 billion years ago when we start forming continents, that's going to move us into the Archaean time period. And remember with geologic time, there's no set, here's the line, let's cross it. It kind of blends together. So that's why we kind of have some shady borders going on here. And you're going to see that throughout geologic time. Every time we have a switch from one time period to another, it's going to be more of a smooth transition, a shady transition, than a, hey, we just crossed this line. It's black on one side and white on the other. There's lots of gray around the transition times. So, sticking with just the yellow, approximately 70% of our continental landmass was formed during this time. So remember, we started forming the crust in the end of the Hadean, but now that crust is forming, and about 70% of the continents come together as continents during Archaean time. Now, they're not going to be continents as we know them. It's going to end up being a giant supercontinent. But they are forming now from those volcanic eruptions, from the magma cooling on the surface. Tectonic plates are going to form during this time, and they're going to start moving and shifting. Remember that magma is highly viscous. We will talk more about that when we talk about layers of the Earth, but that hot molten ball that the Earth is at this time is a very, very viscous. It's almost like a super thick honey, like in between honey and peanut butter, okay, for how much it moves. So you have these tectonic plates, which is the crust, forming on top of it, and they're just going to float there. So this is an image of how continents form. Basically, you have these islands that pop up from volcanic eruptions and that kind of thing, rock that starts cooling. They're going to move around and float on the surface, and as they do, they're going to run into each other. As they run into each other, they're going to join together and form the continental crust. As more and more forms, your crust gets larger and larger. So then you have another island come in, and now it's, instead of hitting another island, it's hitting the continental crust. So they're going to form up that way. You'll have some parts that will go underneath. Sometimes they'll just run into each other and move up and form mountains. But as they slam into each other, they're going to join together. And this is how we form continents. Eventually, it'll look like this with a solid piece of crust. And then you have sediments and things that are kind of flowing out into the ocean. So this is where you'll have like your sandy beaches and that kind of thing. This is a look at where you can find rocks on the surface that date back to the Archaean age. So there's some in Canada. There's a small area here, northern U.S. and southern Canada here on the west. There's lots of them up here in northern Canada, Greenland, all over the place here. You can see Archaean age rocks on the surface if you go to those locations. Okay, back to notes. The oceans start forming about 4 billion years ago. So we're getting our crust forming. We start having a shell around the Earth, and now we have that surface to hold the water so that it does not go down into the molten rock and evaporate. Most of our water is going to come from two locations. Either the volcanic activity putting water vapor out, or comets bringing it in. Remember the big dirty snowballs? They're going to hit the Earth, shatter all the material everywhere, and you get ice particles that fall onto the surface and get melted and become water vapor or water that is liquid. So now we have fresh water forming. Now we can start talking about life. So life requires a couple of things. It has to be organized, and it has to be self-replicating. It also has to be organic. So 3 things you have to have in order to create life. You have to have a container to keep it in. You have to have some type of reactor to tell all the chemicals in the container to work together. And then you have to have some way of copying it. So by developing these oceans, we allowed for a container for all the chemicals. We've got some enzymes mixed in there that have formed that cause the reactions. So those chemicals all work together. And then it eventually developed DNA and RNA, which is a way to replicate itself. So we now have everything we need to create life. And the Precambrian is when we had the first life forms, and they were during this Archaean eon. In order to form the enzymes that were needed to make life, scientists developed what was known as the primordial soup theory for how these enzymes formed. And the way this came about is in the 50s and 60s, they performed a lot of experiments to see if they could make amino acids and get those amino acids to work together to form proteins to start working as a single cell organism. And what they found was they could create cell membranes, they could create simple proteins, they could get this to work by combining just simple atmospheric gases with electricity and heat. So by doing this, they were then able to create conditions that were favorable to creating life. So that gave them their primordial soup theory, and the shallow water from the early oceans, because they were not super deep at the time, allowed all of this to happen. They believe that it started happening near the deep sea vents, which they call black smokers, because these are the volcanic areas underneath the ocean. And again, we started doing this, we started developing life. Originally, it is based on taking in carbon dioxide and producing oxygen as a result, so it's photosynthetic. And it took until about 2 billion years ago before we had enough oxygen in the atmosphere to actually give life as we know it. So, Archaeobacteria are what we're calling these organisms. So they are very primitive forms of life. They live in the deep sea volcanic vents, and they use, they feed on sulfur, and they use that to be their energy source. So they are chemoautotrophs. The reason they were near those vents is because they got chemicals that they needed, they got heat that they needed, they had minerals, including the sulfur that they used for their food. And being deep water, it protected them from the UV radiation from the sun and the oxygen that was forming in the atmosphere above. Eventually, these guys are going to turn into eubacteria and will develop what's called a stromatolite, and the stromatolites are photosynthetic organisms. So they are what is going to provide oxygen for the atmosphere, and it takes a couple 100 million years for them to do it, but eventually they get enough atmospheric oxygen out there that we can start getting more complex life. All of our life during the Archaean Eon is bacterial, and it is known as the age of Pond Scum because it's just filmy bacterial layers. There's not many fossils from this time frame. There's been so much movement in the rocks, and that fossils are fairly easily destroyed. So there are very few still available. They're also very small because they are bacterial. So you have to basically take the rock samples and look at them under very high-powered microscopes in labs in order to find these. So about 2 billion years ago, those stromatolites are working hard. They've been around since 2.7 billion years ago, so they've had a couple 100 million years to put some oxygen out into the atmosphere. We now start having organisms that are able to start using oxygen. We have the capability now because we have oxygen in the atmosphere. We're going to go ahead and move into the Proterozoic Eon at this time because now we have the ability to have complex life. So that's going to be our tipping point that moves us into the next Eon classification. When we move into this Eon, we've got most of our continents formed, and they are formed all in one location as a supercontinent, not Pangaea that you guys are all familiar with, but a supercontinent known as Rodinia. So as these continents form, they collide into each other and become one large continent called Rodinia. As we go through this time period, we're going to look at how eukaryotes have evolved. So we start off with just barely getting that atmosphere with oxygen in it so that we can use it. So early eukaryotes that are around during this time basically took in what we call a mitochondria. So it was a single-celled organism that we call a mitochondria. They were not able to digest it, so they incorporated it. So they can take in these mitochondria, and now they can perform photosynthesis. So these are 2.7 billion years ago, those early eukaryotes before the stromatolites. So by doing this, they can now perform photosynthesis, and they put the oxygen out into the atmosphere. So this is how we get oxygen in the atmosphere. Again, not many fossils. We have rocks that have been destroyed because of lots and lots of movement. It's also mostly squishy things, and squishy things are very delicate. So we don't have a lot of fossils because of that. Proterozoic life is going to evolve during this time frame. And eventually it is going to evolve into the Cambrian explosion and move us into the next eon. This is the end of the notes for today. Go ahead and do your short quiz down here, and we'll see you next time.